Hello, I'm Pete Johnson from Sifos Technologies. In this presentation, we will discuss testing of IEEE 802.3 AT powered devices using the PDA-602A Powered Device Analyzer. The PDA-602A is a third-generation powered device analyzer from Sifos. It is the first member in the PDA600 family of scalable PD test instruments. Introduced in 2016, the PDA602 provides comprehensive 802.3 PD analysis and verification. I will start by reviewing features of the PDA602. We'll then briefly position the PDA602 relative to alternatives for testing powered devices. Next, I will discuss and demonstrate the rich set of measurements and analyses available with the PDA602. Then we will look at the fully automated PD conformance test suite, including a brief demonstration. We will also review the load monitor features, again with a brief demonstration. Next, we will review PoE LLDP testing features and demonstrate those as well. After that, I will review feature scalability of the PDA602 and then wrap up with a discussion of PDA software. The PDA602 provides a robust set of features for analyzing and verifying 802.3 AT PD performance. This feature set makes the PDA602 the only instrument that every 802.3 powered device manufacturer must have. The PDA602 can perform fully automated PD conformance testing on 802.3 AT PDs, that is, both Type 1 PDs that consume up to 13 watts and Type 2 PDs that consume up to 25.5 watts. Between the conformance test suite and the load monitor, the PDA602 enables comprehensive analysis of all critical performance parameters required to ensure interoperability with all 802.3 AT compliant PSEs across all possible connection environments. The PDA602 can flexibly emulate PSEs that utilize 802.3 AT LLDP for mutual discovery and power negotiation while analyzing power device LLDP protocol. The PDA602 offers accurate metering of voltage, current, and power at the PD interface, thus enabling reliable assessment of PD operational characteristics. The instrument flexibly emulates real-world PSE behaviors such as multi-cycling detection and classification prior to power application. The PDA602 is managed from an intuitive graphical user interface on a host PC designed to facilitate rapid setup and analysis. Power sourcing well in excess of 30 watts assures ample headroom for evaluating PD power demand under all conditions. Complex test parameters including waveforms, conformance test reports, and LLDP protocol reports are presented in pop-up spreadsheet reports to enable further offline analyses. The PDA602 is provided with tools for custom test program development, including powerful script automation environment based on Tcl/Tk. The script automation environment is further built upon a binary API library that may be incorporated into other programming languages on a Windows PC. The PDA602 connects to a PC over a USB interface for rapid plug-and-play setup. A separate LAN through port allows a PD to communicate with an external host software during all phases of PD testing and analysis, including concurrent PoE LLDP transactions over the test link with the PDA602. Before elaborating further on PDA602 features, let's briefly consider alternatives for powered device testing and analysis. PSEs are available as very low-cost single-port injectors. While attractive from a cost point of view, this method of testing provides virtually no insight into 802.3 AT conformance parameters, and it neglects the extreme wide variety of behaviors and performance attributes allowed to PSEs under the 802.3 standard. Those who are highly knowledgeable of the 802.3 AT standard appreciate the ineffectiveness of products testing products given PoE technology. Another option for PD testing is a home-brewed system of fixtures and standardized instruments that might include meters, oscilloscopes, DC supplies, protocol analyzers, and other signal sources. While enabling greater insight into critical PD performance characteristics, these setups usually involve high cost to design and develop, and they are resistant to fully automated testing, thus restricting the frequency of testing and hampering productivity. To be effective, a comprehensive understanding of the 802.3AT specification is required. The PDA602 provides high defect and PICS coverage that is highly automated, requires just one instrument, making just one LAN cable connection to the PD under test. A new user can be reviewing detailed PD conformance reports in less than 20 minutes. Further, the PDA602 can be price performance scaled for engineering, QA, and manufacturing applications. I'm now going to connect the PDA600 to a PC and connect the test port to a PD. I will then open PDA Interactive software so that we can observe PDA600 measurements and testing features. PDA Interactive serves as a virtual front panel to PDA600 instruments. One or more PDA600 instruments must be connected via USB to the host PC prior to opening PDA Interactive. Before getting into PDA602 measurements, we'll take a look at the DC source features. The PDA602A can power a PD with a user-specified voltage between 28 and 57 volts. This voltage is applied to one of four possible quadrants: Alt-A MDI, Alt-A MDIX, Alt-B MDI, or Alt-B MDIX. This represents either pair set with either positive or negative polarity. A slow ramp mode is offered for manual assessment of PD turn-on and turn-off voltages. Generally, when powering a PD, the PDA602 will first classify that PD using physical classification. This classification can be specified as a single event, that is, one class pulse, two event or two class pulses, or none to bypass classification altogether. Type 2 PDs interpret two-event classification as an authorization to exceed 13-watt loading. Given the two-event configuration, users can also specify the mark time between the second class pulse and the application of DC power. This enables margin testing of Type 2 PDs that must retain memory of the class pulse count. Now we'll take a look at unpowered measurements. The PDA602 performs detection resistance measurements with 1% accuracy in each selected quadrant. Measurements can be cycled for averaging, as well as to emulate PSEs that under power management control cycle detection repeatedly prior to a power-up. A detection signature may also be measured on the unpowered pair set. Type 2 PDs are required to present non-valid signatures on whichever pair set, Alt-A or Alt-B, is not powered. Because these measurements include resistive effect of PD's front-end bridging, they equate to how PSE assesses signature validity. Detection capacitance measures the effective input capacitance of an unpowered PD. The PDA resolves this with 2.5% accuracy, including any effects of front-end bridging. The class metering applies one or more classification pulses and returns the load current that communicates PD classification. Current is measured with approximately 2% accuracy. Given two-event classification configuration, the meter also returns the mark region load current. Just like detection measurements, classification measurements can be multi-cycled to report average or final cycle measurement results. The PD conformance test takes advantage of these features to assess impact of sequential detections and classifications on the measured class value. I'll now perform some DC meter measurements on the Alt-A pair set with MDIX polarity selected. First, I'll measure detection signature resistance, averaging 5 cycles of the measurement. Nominally, this should read 25 k ohms. Next, I'll perform just a single detection signature capacitance measurement. This value should not exceed 0.12 microfarads. Finally, I will measure the classification signature of this Type 2 PD using two-event classification. This measurement would nominally indicate 40 milliamp load current on each class event and a between-class discharge load in the range of 0.25 to 4 milliamps. The PDA602 offers 4 static DC measurements applicable to a powered PD. PD input voltage is sensed at the output of the test port and offers 0.75% accuracy with 0.1 volt resolution. PD input current is measured from 1 milliamp to 1 amp with accuracy of 2% at low currents and 0.75% above 100 milliamps. PD input power is measured with approximately 2% accuracy and 0.1 watt resolution up to 50 watts. PD backfeed voltage measures the DC voltage appearing on the unpowered pair owing to leakage in the PD. In addition to static DC measurements, the PDA602 also offers a selection of waveform traces useful for observing dynamic loading behaviors. Waveform traces can be configured with sampling intervals of 0.2 milliseconds to 20 milliseconds. As with DC metering, sensing is performed at the MDI, that is, at the PD input. All trace data is presented graphically in Microsoft Excel spreadsheet reports. Voltage and PD load current waveforms can be configured to produce 1,280 samples. The maximum possible trace duration at 20 millisecond sampling is 25 seconds. Power and combined voltage plus current traces offer up to 640 samples covering 13 seconds of time. Voltage plus current traces show the dynamic relation between PD current load and PD input voltage. Waveform traces may be immediately triggered from software, or they can be triggered by hardware events such as start of PD classification, power up, power down, and upon load current or load power excursions beyond a user-specified threshold. Waveform measurements are performed with the same accuracy and resolution as DC meter measurements. To demonstrate the trace meter, I will configure the PDA to power a Type 2 PD to 42.5 volts, preceding the power-up with a 2-event classification. I will configure a 300 millisecond delay from the second class event until the power-up using the Mark II setting. I will then measure load current by selecting the current trace, specifying a sampling rate of 2 milliseconds per sample and a trace duration of 300 samples or 600 milliseconds. I then trigger the trace on the start of the PD classification by the PDA so that we can observe both classification and power-up load currents. Pressing the arm button then arms the trace. Pressing class and power then initiates the whole process. The waveform trace appears in a pop-up Excel spreadsheet report where we can observe the classification process including the 300 millisecond delay, and we can see power-up load currents. All of the raw time sample data is stored on page 2 of the report. The header on page 1 includes minimum and maximum trace values and associated time points. A third category of PDA602 measurements is the streaming trace. Like waveform traces, streaming traces result in graphical pop-up spreadsheet reports. Parameters reported include power, current, and/or voltage. Streaming traces are software or user-triggered and can capture data over much longer periods depending on user configuration. Sampling is configurable to 5 or 10 milliseconds and maximum trace duration is about 3 hours. Once a trace report opens, users may select what parameter or parameters are graphed. Via the switched LAN port, users may also be manipulating PD states and functions while the streaming trace runs. Streaming traces automatically provide PD classification policing. That is, they report any instances where the load current and load power exceeds a PD's classification. So by default, streaming traces start by classifying the PD under test. Violations are reported in 3 categories: average PD power draw, peak PD power draw, and window violations where class power is exceeded for more than 50 milliseconds. The PD conformance test offers fully automated one-button PD testing to assess many critical PD parameters relative to IEEE 802.3 specifications. The test suite can be configured to test Type 1 PDs and Type 2 PDs. Type 2 PD testing may be performed with 2-event PSE emulation and/or with LLDP PSE emulation. Normally, Type 2 PDs should be tested with both forms of PSE emulation. Test coverage can be configured to specify quadrants, that is, pair sets and polarities that will be evaluated. There are 2 categories of testing within the PD conformance test suite. Passive tests include measurements of the PD prior to power and during power-up, while powered tests focus on PD parameters after power-up. More specifically, passive tests assess PD signature characteristics, including responses to various PSE detection and classification sequencing behaviors, as well as turn-on and turn-off voltages. Powered tests cover initial and steady-state loading, responses to single versus multi-event classification, and, if specified, PoE LLDP protocol behaviors and responses to LLDP dialog with a PSE. Testing may be automatically repeated up to 10 cycles for the purpose of evaluating parameter repeatability and capturing rare intermittent behaviors of a PD. When PD conformance testing is completed, a colorful pop-up Excel spreadsheet annotated with any failures or warnings is automatically produced. The spreadsheet includes 1 page per quadrant tested. In this next demonstration, I will test a Type 2 PD for passive parameters in all 4 quadrants, then for powered parameters in just 1 quadrant, evaluating responses to powering with Type 1 PSEs and then with Type 2 PSEs that utilize 2-event classification. To do this, I select all quadrants under passive tests and then select just Alt-A MDI under powered tests. I will also enter the type or model of PD I am testing for reporting purposes. Under powered tests, I select that this test run will include both Type 1 PSE and Type 2 2-event PSE modeling. I also select the desired source voltage to the PD from both Type 1 and Type 2 PSEs. In this case, I have chosen to use lowest possible source voltages the PD can expect to see from a Type 1 PSE, that is 37 volts, and then from a Type 2 PSE, namely 42.5 volts. I also can select the desired dwell time, that is, the duration over which power draw metrics will be acquired following power-ups. In this case, I'm choosing 30 seconds. Now that all the test coverage is configured, I just press the Start Test button to run the PD Conformance Test Suite. After a period of time that is dependent on the selected test coverage and the powered-on dwell times, the PD Conformance Test report opens. The first tab on the report is the Alt-A MDI quadrant. Here, we tested both passive and powered parameters. Passive parameters are provided under the detection and classification and the power-up-down subheadings in the report. Powered parameters then appear in each of the remaining subheadings. The other test report pages present the passive test parameters for the other 3 quadrants, namely Alt-A MDI-X, Alt-B MDI, and Alt-B MDI-X. A note page in the standard report provides some detail regarding each parameter included in PD conformance testing. Many are referenced to specific parameters and requirements in the 802.3 specification. The PD tested here produced some warnings in the area of PD inrush and also produces some failures for drawing too much power, that is, more than 13 watts, given a PSE that does not provide 2-event classification. The inrush warnings are related to both magnitude and timing of initial inrush load. For many PDs, full PD conformance testing cannot be achieved with the PD conformance test alone. PDs that present varying load conditions depending upon operational states, interface conditions, and network controls must be analyzed over periods of time where all of those conditions are exercised. Both steady-state power draw and load transients must be continuously observed to assure that the PD does not create a condition that might cause a PSE to remove power. The load monitor provides continuous real-time sampling and display of both instantaneous and average PD power draw. Sampling is performed either at 5 millisecond or 10 millisecond intervals. Power draw is sensed at the PD input and presented on a chart recorder-like display. The PD may be manipulated over the network via the PDA LAN interface while the load monitor is running. Additionally, PoE LLDP negotiation and updating may also run concurrently with the load monitor. As the load monitor runs, it continuously checks the average power allowed to the PD based upon PD classification and any subsequent LLDP negotiation. It also checks peak power relative to the allowed maximum peak power, and it evaluates for window violations where maximum average power is exceeded for more than 50 milliseconds. The load monitor will immediately enunciate these 3 violation types and will optionally stop running on violation. Raw sample data collected by the load monitor may be exported to Excel for further post-capture analysis. I will now demonstrate the load monitor working with a Type 2 PD that produces 2 types of load power violations. First, to open the load monitor, I will select Stream Trace, then Load Monitor. I will then set sampling to 5 milliseconds and press Open to open the load monitor window. When the load monitor opens, I select 2 classification events in order to grant the Type 2 PD full power following the power-up. I then set the source voltage, V-port, to 42.5 volts, again recreating minimum possible source voltage to the PD. Pressing Start activates the load monitor, whereupon a PD classification is performed followed by a power-up. The load monitor then continuously measures both instantaneous and average power. Because of the 2-event classification here, the PD is entitled to an average power of up to 25.5 watts and a peak power up to 28.3 watts. After a short period of time, 2 power violations are discovered. First, the PD exceeds 28.3 watts for a brief 20 millisecond interval. Shortly thereafter, the PD exceeds 25.5 watts for longer than 50 milliseconds, thus creating a window violation. Details of the sampled data and timing are available in an Excel spreadsheet if Display Trace is pressed after the load monitor is stopped. The PDA600 includes an optional subsystem to fully emulate PSEs that conduct Type 2 LLDP power negotiations with Type 2 PDs. From an LLDP point of view, the PDA embeds a PSE that manages link layer communications with the PD under test. The PD test report may be configured to 10, 100, or 1000 base T, or it may be auto-negotiated. This allows PD power draw to be evaluated with the various link rates. Remote LAN communications with the PD for purposes of control and traffic emulation may be conducted using the PDA LAN port while the 802.3 LLDP dialog concurrently takes place. The PDA600 can flexibly emulate different LLDP behaviors of PSEs, including control of protocol content and protocol timing. It can even emulate PSEs that are overly slow in responding to PD power requests. Like waveform traces and PD conformance tests, LLDP protocol analysis can be routed into colorful Excel reports that enunciate any protocol and timing violations on the part of the PD. LLDP protocol traces include power-up traces and power adjustment traces. To demonstrate the capture of an LLDP power-up protocol trace, I will first configure power to Alt-A MDIX, then open the LLDP tab menu in PDA Interactive. In the LLDP menu, I specify that we are emulating a Type 2 or 30 watt PSE that will grant up to 25.5 watts. That is, it has at least 30 watts available at the PSE output. I will also specify that the PSE will grant only the requested power from the PD and no more than that. I then configure the trace to run for 30 seconds and set a 5-second PSE LLDP transmit interval so that we can produce high packet density. Finally, I specify that the PSE will respond to new power requests from the PD 4 seconds after receipt of those requests. I then press the Power Up Trace button to start the protocol recording. The PDA600 powers the PD and looks for the PD to link up and transmit an initial power request. The PD transmits a valid 13-watt request while it waits for information from the PSE. The PSE sends LLDP messaging indicating that it is Type 2. This allows the PD to now request 20.3 watts. After 4 seconds, the PSE acknowledges the 20.3 watt request and grants that power to the PD. At this point, both parties acknowledge the 20.3 watt power allocation. The trace terminates at 30 seconds. I then press the View Report button to open the Excel spreadsheet report for LLDP protocol analysis. In this instance, the PoE LLDP protocol is fully valid in packet structure, packet contents, and packet timing, so no violations are annotated in the report. The PDA602 can be scaled to offer the best price performance point to each PD test application and environment. The base instrument offers analysis of Type 1 or 13-watt PDs. This includes sourcing with single event classification, DC meters, and trace metering. It fully supports scripting and program automation required for manufacturing environments. The base instrument can be upgraded to Type 2 PD analysis with a field-activated license key. This enables 2-event classification so that Type 2 PDs can operate up to 25.5 watt loading. The PDA600 can also be upgraded via license key to access the automated PD conformance test, streaming traces, and the load monitor for full PD specification conformance analysis. The conformance test will test Type 1 PDs, and if the instrument is licensed for Type 2, it will also test Type 2 PDs. Finally, the PDA600 can be upgraded to support PD LLDP testing and analysis. This feature requires the Type 2 license, and it also enables LLDP powered on testing in the PD conformance test suite and LLDP power negotiation during load monitoring. The PDA600 includes PDA software for a Windows PC. The PDA connects to the host PC across a USB 2.0 interface. Up to 8 PDA instruments may be connected to a single host PC via USB connections. PDA Interactive is the graphical user interface software for the PDA600. It provides the virtual front panel that was seen earlier throughout this presentation. PowerShell PDA is a Tickle-TK scripting shell for the PDA600. It provides high-level commands, interactive control, and easy debugging of automation programs involving the PDA. PDA Interactive is built on top of PowerShell PDA. The PDA600 also includes a binary library or DLL that can be integrated with many Windows-based programming environments to provide control of PDA600 functions. This library forms much of the foundation to the PowerShell PDA programming shell. As described earlier, PDA Interactive, depending on licensing features, offers up to 3 tab menus. On all configurations, the Analyze tab menu is used to configure connections, DC sourcing, and classification. It also supports DC meter measurements and waveform trace measurements. Stream traces and the load monitor are available with the PD Conformance Test license. Also available with that license is the Test Suite tab menu. The PD Conformance Test is configured and run from this menu. Finally, the LLDP tab menu is available given the LLDP license. This menu is used for configuring and running LLDP traces based on LLDP dialogues that negotiate power with a PD under test. The PDA602A is the first member of a family of power device test instruments. The next member of this family will support 4-pair PD connections and powering with 4-pair power capacity to at least 100 watts. This instrument will mimic a dual-channel PSE that can monitor and report on Alt-A and Alt-B pair sets independently with sensing at the PD interface. To meet the needs of 802.3bt, it will include connection check features as well as flexible multi-event classification. To meet the needs of emerging enterprise wireless access points, it will support a flow-through LAN channel for LAN links such as 2.5G base T and 5G base T. Future PDA600 instruments will be fully backward compatible with the PDA602A for testing Type 1 and Type 2 PDs. Thank you for watching our presentation of the PDA602 Powered Device Analyzer. We hope that you will agree that the PDA602A is the only instrument that every 802.3 PD manufacturer must have in order to assess PD designs and to verify manufactured PDs.